Hi, everyone. I'm Shubha, and very much welcome to Jason's talk on acceleration by stepsize hedging. So Jason Altschuler is an assistant professor in the Department of Statistics and Data Science at UPenn, where he is also a member of the Department of Computer Science by courtesy, the PRIML Center for Machine Learning, and the Warren Center for Networks and Data Science. Previously, he received his undergrad degree from Princeton and his PhD from MIT, where he received the Sproul's Award for the best MIT thesis in AI and decision making. His research is at the interface of optimization, probability, and machine learning, with a focus on the design and analysis of large-scale optimization algorithms. So Jason, please go ahead with your talk. And thanks very much for giving it. Yeah.
Thanks very much. OK, good. So this talk has two main takeaways. The first one is a result, which that if you're careful about how you choose step sizes, this can actually buy you quite a lot. The second main message of today's talk is the main algorithmic mechanism, something we call hedging. I'll tell you what that is soon, but you can intuitively think about it as a very non-greedy approach to algorithm design. So hopefully, by the end of the talk, you know why I put this pithy quote in, aside from the nostalgia reasons that this was the preface of my old master's thesis back when I was here at MIT. OK, so let's get started. The premise of today's talk is very simple to state. The question is this: can you accelerate gradient descent? Can you make it go faster just by changing step sizes? So don't change the algorithm in any other way. No momentum, no internal dynamics. Just can you make it go faster by just changing the step sizes? A little background first. So what is gradient descent? So here at ORC, everyone is surely very familiar with gradient descent. Here's, it and its variants are the primary workhorse of much of modern machine learning, engineering, et cetera, et cetera. Here's a cartoon. So my search space here is going to be in one dimension. These are my different decisions x. I'll draw a nice convex function f of x. The basic goal in optimization is to find a minimizer x star. Gradient descent is a simple iterative algorithm which tries to do this. In each iteration, it maintains a state, a guess, x sub t of the minimizer. And in each iteration, it tries to improve this guess by moving in a direction of descent. So a direction, the negative gradient. So it moves a bit in that direction. Here, you move to the right. And you form your next guess, xt plus 1, and you repeat. The only parameter in this algorithm is how far do you move. So this is the step size alpha t. Or if you're fashionable these days, you call it the learning rate, same thing. That's the only parameter in this algorithm. And the question we're interested in today is just how do you choose this parameter? How do you choose the step sizes so you converge as fast as possible? Of course, to say anything concrete, we have to say anything quantitative, we have to restrict to a concrete setting, a setting where your functions have controlled curvature. So today, for simplicity, we'll talk about strongly convex and smooth functions. This is just for simplicity. The same results and conceptual ideas extend to other settings. For example, if you remove strong convexity, everything is conceptually identical. So what is strong convexity and smoothness? Strong convexity means your function is not too flat. Smoothness means your function is not too sharp. The way we typically write this, is this too small for people in the back? OK, great. The way we typically write these things is lower spectral bounds on the Hessian. So strong convexity here would be little m. Smoothness would be the big M. What matters here is how different these two bounds are. And the right way to measure how different these two bounds are, which is the richness of the function class, is the ratio, this thing called the condition number kappa. This is the right scale invariant quantity that measures how rich your function class is. If kappa is larger, then your function class is richer, which means it's harder to uniformly optimize over all those functions. OK, so this is our function class. How fast can you make gradient descent? How fast can you go? How should you choose your step sizes? So if you open any textbook on convex optimization, like Polyak's book, Nesterov's book, here at MIT, so Asu and Dimitrius's book, you'll see that they all prescribe the same thing. They all prescribe using constant step sizes. which means in each iteration t, you use the same step size alpha t. There's some explicit number for which number that is. If you tune it the best way, the good thing about this is it converges. The bad thing is it converges slowly. In fact, people often call this convergence rate the slow rate or the unaccelerated rate. So quantitatively, it takes you roughly kappa iterations to converge, or even to start converging. So when your function class is rich, meaning kappa is large, it takes a long time to start converging. And so there's been a long line of work to try to develop faster algorithms. Algorithms that are faster are called accelerated algorithms. So here's a table to provide some context. So a key point in this table is that there's a huge difference between the general case of convex optimization on the right and the special case, sort of much simpler case of quadratic optimization, convex quadratics on the left. In particular, so what makes quadratics simple? Well, if your function is quadratic, then your gradient is linear. So a gradient descent step is linear, which means, and we'll talk about this in more detail soon, but roughly this makes multiple steps of gradient descent a simple polynomial expression. And these connections let you achieve accelerated methods in a number of different ways for the quadratic setting. We'll talk about this in more detail soon, but this is just because there's many equivalent ways to describe polynomials. So for example, one way to describe a sequence of polynomials is through three-term occurrences. That gives rise to momentum-based methods, like Polyak's heavy ball algorithm. You can also describe polynomials by their roots. This gives rise to Chebyshev step sizes due to Young. You can also describe polynomials through orthogonality. This gives rise to conjugate gradients, also from the 50s. So there's many ways to do acceleration in the special case of quadratics. To some extent, this is all very classical, but before my parents were born. The key question is, how do you extend these from the quadratic case to the convex case? Because we'll talk about this later, but everything in this setting really relies on the linearity of one step, which lets you have these polynomial correspondences. In the convex setting, your gradient is nonlinear, and that whole story breaks down. So it was a major breakthrough by Nesterov in the 80s when he was able to get accelerated rates for the first time in the general convex setting. There's been a lot of work in the decades since, so this is very much not a straightforward extension of the quadratic setting. Let me emphasize that Nesterov's fast gradient method, so the thing here. Hey, Rob. And all the other algorithms that are accelerated since, they actually change the algorithm by adding momentum or internal dynamics or things that are really beyond just changing the step sizes. So what today's talk is about is, can we get acceleration, this sort of basic question, can we get acceleration by just changing step sizes without changing the algorithm in any other way? Are there step sizes beyond this constant step size schedule that improve over this by a constant factor, by an asymptotic factor? Is this the right rate, O of kappa? Can you get all the way down to root kappa? Is the answer somewhere in between? How fast can you go? So everything in this talk will be about this one cell. Okay, so we'll build up to this in several pieces. Let's first go back to the constant step size schedules. Why is this the standard prescription? So if you look at any of these textbooks, they'll say, don't just use a constant step size, also this is the best step size. It's some explicit number, 2 over big M plus little m. The details don't matter. It's explicit. The thing that does matter is why they choose this particular number. There's a good reason. It leads to the best one-step contraction rate, the best R1 here. So this inequality here is the key inequality in all the standard proofs of gradient descent. It's so important I'm actually going to write it on the board. We'll come back to it several times. Okay, so what does this inequality say? It says that in each iteration, if I go from point x0 to x1, my distance to optimum contracts, it shrinks. Why? Well, because this R1 is less than 1. What is it exactly? It's some explicit number, kappa minus 1 over kappa plus 1. The details don't matter. The point is this is less than 1, so you're actually getting closer. And so the way that all the standard proofs go is they'll say, well, if I'm shrinking in one iteration, then I can do this twice, for example. And so now if I go from x0 to x1 and then x1 to x2, I can get the same contraction twice. And you improve by a bit more R1 squared. You can do, of course, the same thing to say this is now, if you have xn, of course, this is now to the power n. And after n steps, you have this much progress. Right? So this is why this R1 is so important to make this as small as possible. This determines your convergence rate. I will refer to all proofs of this type as greedy or one-step analyses. Because what they do is they greedily look at the progress in a single step and then combine this progress multiple times, but separately between the steps. Okay, we'll come back to this later. But this already tells you why it's important that R1 is as small as possible. And the reason, as I mentioned before, that you choose this step size alpha bar is because it leads to the best R1. Indeed, if you choose a shorter step, so if alpha t is smaller, then there's some functions which you would undershoot. You wouldn't make enough progress, and your R1 would be worse. Similarly, if you choose a longer step, you could overshoot and have a worse R1. So this alpha bar here is chosen as just a sweet spot that equalizes between these two worst cases and gives the best R1. Okay, so you can do that tuning. This is an explicit number. As I mentioned before, the good news is this converges, but the bad news is this converges slowly, the slow rate I mentioned before. This is exactly the O of kappa rate. Of course, in the years since, there's been many other stepsize proposals, a lot of work on, for example, on Riju-Goldstein rules, Poliak rules, BB rules, etc. But in short, before we started working on this, there was no analysis that any stepsize schedule could improve by any amount, even by a constant factor, over the slow rate, the constant stepsize schedule rate, for any setting beyond quadratics. Okay, so in other words, this cell here, it was unclear whether there's any benefit over using the constant step sizes above. So let's first try to understand why there was an opportunity in the quadratic case. Why in the quadratic case could you optimize step sizes to get anything better? These analysis techniques will not directly extend, but hopefully we can build some intuition to develop stuff for the convex case. Okay, so let's turn to quadratics, and we'll look at why there's an opportunity for using non-constant step sizes in the simplest possible setting. So 2 step sizes, n equals 2. And this will just follow the classic analysis to Young's paper in the 50s. Okay, so here we're in the following setup. Our function will assume to be quadratic. If you translate without loss of generality, shift, we can make f a quadratic form, just for simplicity. The strong convexity and smoothness amount to saying your Hessian, which is now this features H, is spectrally bound between little m and big M. Okay, and the question we're interested in is, what are the best step sizes? So we'll use alpha first, beta second. If we find the best possible step sizes, will they be constant? And if they're not, do we get any better rate than the constant step size schedule? Okay, so we're finding the best possible step sizes, and here is the rate for alpha and beta. I'm just calling it R of alpha beta. This really should play the role of, we'll put this back to 2, so we'll talk about 2 for a while. This will really play the role of R2, which we'll say is the best possible bound here. The question, another way to say can you do better than constant step sizes is can you do better than R1 squared? A bit more concretely, how do you measure this? Well, this is the worst case convergence rate. So you look at the worst case function, the worst case initialization. You ask what's the convergence rate you could prove. And as an aside, This setup is very flexible. Here I'll mention contraction in the x iterates, but the same thing works for gradient iterates, function value, nothing changes. Okay, so I'd like to go through the derivation at least briefly, because I think there's some insightful things about that we'll see. Okay, so here's the analysis due to Young. First thing you should do is start with a definition. It's always a good starting point. So, definition of gradient descent. We use step size alpha in the first step. Because f is quadratic, the gradient is linear. So if you just factor things, you can write x1 as a simple linear update of x0. Of course, you can do the same thing for x2 in terms of x1. If you combine these two, you can write the final iterate x2 as a function of the initial iterate x0. And something important to notice here is this final output depends on the step sizes alpha and beta only through a single statistic, only through this polynomial p of h, this polynomial here. So instead of optimizing over the best possible step sizes, we can also think equivalently of optimizing over the best possible polynomial, because from the polynomial we can recover the step sizes, take the inverse roots. There's a correspondence. So a little bit more concretely, instead of looking over all the possible step sizes, alpha and beta, we can look for all the possible polynomials it would generate. These are all degree 2 polynomials, so degree 2 because you have 2 steps, with this normalization condition, just because there's always an I and an I. So instead of looking at the best step sizes, we'll now ask what's the best polynomial p satisfying this normalization. So we need to write the rate in terms of this polynomial so we can optimize over the polynomials. If you do that, so here I'm just taking this rate function up here, rewriting it in terms of the polynomial. So x2 is p of h x0. Let x star be 0 without loss generality. And you just simplify in 2 steps using some basic properties of spectral norm. So definition of spectral norm cancels out the x0s. If you diagonalize, you get this quantity. The details aren't so important. The main point is now we need to look at the best, again, degree 2 polynomial with normalization constraint that minimizes this objective. And the good news is once you put it in this form, you can open any textbook on approximation theory, and they'll all tell you that the optimal polynomial is this one. Okay, so what makes this polynomial good? First of all, it's degree 2, so it's feasible. It also satisfies p of 0 equals 1. That's the other feasibility criteria. What makes it good is that it's squeezed as much as possible around 0, as small magnitude as possible in this interval little m to big M. For the experts in the room, this constraint, this optimal value is achieved at 3 points, which is just the extremal characterization of Chebyshev polynomials. And once you have this polynomial, there's some technical details to this, but the main point is once you have this polynomial, you can take out the best step sizes, right? You just take the inverse roots. There's some explicit formula for them, a little bit complicated. The details don't matter. The main point is these are 2 different numbers. Why? Well, this polynomial has 2 different roots. Those roots are not in the same place. And if you remember how we construct the polynomial, the step size are the inverse roots. Okay? So 2 main takeaways from all this. There's some technical details, but the main things I want you to take away is first, what do we just do? We just optimize over the best step sizes, and we realized that the best step sizes were not constant. It was helpful to take one short one and one long one. It popped out of the analysis that there's actually an advantage of not using the same step size twice. And this is actually strictly better because if you do the details, you get an R2, which is strictly better than R1 squared. The second takeaway is that, well, this argument was it really used linearity of gradient descent. That's linear in one iteration. To have this polynomial connection, everything really relied on polynomials. In the general convex setting, the gradient's nonlinear, and this whole connection breaks down. So it's not clear at all how much of this story should extend, and if so, how you would extend it. But at least we have some intuition that there's some opportunity, perhaps, for trying to be clever with step sizes to get faster acceleration, to get faster convergence rates. And we'll build upon that for the convex setting in just a minute. But first I want to dive a little bit deeper into this first takeaway, into why there is an advantage for non-constant step sizes. Okay, so first of all, you might be wondering, okay, so like 10 minutes ago I told you that the best constant step size was some specific number, and I gave you, a plausibility argument, or a reasonable argument for why you wouldn't want to deviate from that. Why is that not in contradiction with the fact that we have two different step sizes here? So there is no contradiction, and to understand this, you need to go into a little bit more detail for why alpha bar was the best step size for the one-step rate. So before I argued that a shorter step could lead to worse contraction rate, a long step could also lead to worse contraction rate. What's important is to go one step further and to realize what that means. So what that means is that there is some worst-case function. So if you choose a short step, there's some worst-case function which you don't make much progress on. And if you choose a long step, there's another worst-case function. Turns out to be different. What function that is doesn't really matter, but it's a different function that penalizes you. And so what the opportunity really comes from here is that the worst-case functions can't align. And by looking at multiple steps in your analysis at once, you're protecting yourself from that. Okay, so that's why in a single iteration you might not make much progress, but overall your progress could be better. Let me flip that on its head in one way just to drive home a really important point. To argue that the worst cases can't align, it's really important that you look at you analyze the progress of all the iterations at once, that you don't do this one-step analysis, this greedy one-step analysis, looks at each iteration by itself. This has no idea that the worst cases can align. In fact, any argument like this will not only give you the wrong bounds, but even worse, when you optimize to find the best step sizes given these bounds, they'll give you the wrong prescription. They'll tell you should use constant step sizes. That's why we had the standard prescription from before. Okay. So again, this is all intuition that there are, at least in the simplest case of quadratics, there could be some opportunity. Now we'll move to the convex case. Any questions at this point? Yeah, Alex.
The young prescription, do you alternate between those two step sizes, or what's the actual schedule?
Good. So for the two-step thing I mentioned before here, you'll notice that this polynomial, it doesn't matter the order of alpha and beta. Everything's commutative. So actually, you can take these two roots. You better take these numbers, but which order you take the numbers doesn't matter at all. The same, if you want to do n-step schedules, you can do exactly the same analysis. The optimal polynomial will be the degree n Chebyshev polynomial instead of degree 2. You take its roots. They're explicit things in terms of cosines. And you can permute them in any order. The order doesn't matter, at least for convergence rate, assuming exact arithmetic.
So if you're actually implementing this, you have to know ahead of time how many iterations, right?
There's a longer story there. If you do exactly for this Chebyshev thing, then as written, yes, you would want to know the number of iterations. There's various hacks, like turns out they sort of interleave at scale 2n or n. There's ways of doing an IID. There's ways of doing momentum methods that are actually stationary, that don't change. But yeah, good question. Any other questions before we move to convex? Great. Okay, so this all suggests that there might be some opportunity. I mean, the short and long steps come out very naturally from the analysis of quadratics. It was clear, why there was some advantage. It might suggest that there, in the more general case of convex functions, there might still be some hope for short and long. But before we started working this, it was unclear if any step. It was unknown if any stepsize schedule led to any speed up, even by a constant factor, over the constant stepsize schedule, the slow rate, for any setting beyond quadratics. And there's sort of two main difficulties here. Let me say the second one first. So I've already alluded to this. It's essential, if you want to do any speed up over the constant stepsize schedule, it's essential that you don't do a greedy analysis. It's essential that you look at the analysis of multiple steps together. The reason this was tractable in the quadratic setting is because you could understand this multiple step descent through a polynomial. And that whole story breaks down beyond quadratic setting. So it's at least a technical barrier. But let me also mention that it's not just a technical barrier. There's actually fundamentally, this problem is quite different. So for example, if you run Chebyshev step sizes, the things that are good for quadratic, this actually diverges in the convex setting. The order actually does matter, back to Alex's question earlier, for the convex setting. So there's a number of phenomena which are fundamentally different when you go beyond quadratics. But let's try anyways. Let's see what would happen if we optimize the best two step sizes for the convex setting. So we'll do exactly the same setup. The only difference is now our function f is not quadratic. So again, we optimize over best step sizes alpha, beta. We look at the worst case convergence rate. The only difference, this function f is now over this entire set of convex functions, or strongly convex and smooth. Okay, so the first question we've already alluded to, how would we analyze this? Like, forget about even optimizing step sizes. How would you prove a convergence rate for a fixed alpha beta? We've said before that none of the greedy analyses would work. This is, I guess, a natural way because it's tractable to understand the one-step progress. But we have to go beyond that. We've said we have to look at the progress in multiple iterations together. And remember, the reason for that is we need to ensure that the worst cases can't align, that you can't have a bad function for the first iteration, which is also bad for the second iteration, and so on. And so what we need to do is we need to enforce exactly that the function cannot align in bad ways in each iteration. So we need to enforce long-range consistency conditions that whatever the function looks like at iteration 1, iteration 2, iteration 3, it can't always misalign. So this question brings us to classical things from convex interpretability, dating back to Rockefeller's work on cyclic monotonicity, if you've heard of that. If you haven't, that's fine. These conditions were put into more computationally friendly way by Jorgen Tabul and Taylor Dahl, some very nice papers in the last decade. What these inequalities are, these are all the long-range consistency conditions at every point xi and the corresponding gradient gi. So for each pair of iterates, I and j, so I and j are indices of your iterates, iteration 0, 1, 2, and also star. You also need to enforce the optimum doesn't move around. These are inequalities in every pair of iterates. What the inequality is some sort of nasty quadratic. The details don't matter for us today. Let's just call this qij. This is called the co-coercivity. And the nice thing about this is if you enforce that qij is non-negative for every pair, this captures all the possible misalignment constraints. Or if you flip that, if you think about the dual perspective, these are all the valid inequalities that you could ever use to prove a convergence rate. Okay, so if we combine these in different ways, we can get some type of proof. Okay, so how do we combine these for two steps, and what do the optimal two step sizes look like? So here's a screenshot from my old master's thesis back when I was here at MIT. And this gives you the optimal two step sizes for the convex and strongly convex and smooth case. So back then I called the two step sizes eta 1 and eta 2 instead of alpha and beta. But these are the optimal two step sizes. The exact formulas are a bit complicated. They don't matter. The only thing that matters is these are different numbers. These are not constant step sizes. The theorem says that this gives you some rate. This is R2. Again, the formula is somewhat complicated, but it's explicit. And the main point is this is less than R1 squared. This is provably better than the one-step analysis. How do you prove it? Well, the theorem actually gives you a proof. The theorem writes this identity. This is an equality. This is just a fact about gradient descent. You write the stuff on the left-hand side as equal to the stuff on the right-hand side. The right-hand side is the sum of these multipliers, lambda ij. These lambda ij's have somewhat messy formulas. For now, let's just say it's magic, but it's not magic. There's a simple place where this comes from. These lambda ij's are all non-negative. That's the important point. And these qij's, we just said are valid inequalities. So for any convex function, this strongly convex smooth function, these are non-negative. So the right-hand side is trivially non-negative. And what this implies is that, if you rearrange things, x3 minus x star squared is greater than r2 squared times x1 minus x star squared. Okay, and let me take out the squares everywhere just so we have a little bit more syntactically similar. This is exactly the same thing that we were writing before. This is a better two-step analysis by looking at the two steps together. I haven't told you yet how to find these step sizes, how to find those lambdas. That'll come later. Sorry? Ah. Yeah, that's important. Thank you. Well, up to some negative signs, this is a fact. Thank you. Okay, let's fix that. So this is greater? Yeah, that would help. Okay, and back then I also called x3 and x1 your iterations of 0, 2. I started indexing 1, but otherwise it's the same thing. Great. So we'll talk about doing this for general n steps in just a minute, but first I want to keep talking about this two-step schedule because there's a number of phenomena that come up here that are fundamentally different than the quadratic case, but are the same for general n. So I think it's worth, there's some interesting things I like here. Okay, so the first thing is that the order matters. It's important you choose a short step first and then a long step. The order did not matter for quadratics. Okay, I've already mentioned the second thing, that this rate is strictly better than R1 squared. So there's some advantage of using non-constant step sizes. And something else that I think is interesting and very intuitive is that if you look at the convex, these short and long from the convex, they are, well, short and long, but they're not as short and not as long as the Chebyshev step sizes. And there's a good reason for that. The class of convex functions is, of course, richer than the set of quadratic functions. And so when you're hedging, when you're doing aggressive steps, you have to be more careful. So for convex functions, you can't quite be as short or as long. You can't be quite as aggressive, and that's intuitively why you might expect some this sandwiching. This will lead you to a not quite as good a rate, and we'll see later how much acceleration do you actually get. But at least this gives you a constant factor. Okay, and I'll mention here is a nice picture I like that here I'm drawing a contour plot. So alpha is the first step size on one axis. Here little m is 1 and big M is 4, I think. Beta is the other axis. And the rate, the third dimension, which I'm just drawing as a contour plot, is the worst case rate for that alpha and beta. So you'll see that the quadratic on the left, the best step size is here or here. And these are symmetry because the order doesn't matter. Whereas for the convex case, you have only one step size, it's short and long. It's not quite as short, not quite as long. Just a picture showing what I've said before. We're ending at 5:15, right? Okay, perfect. So we have plenty of time for questions if anyone wants to be brave on a recorded talk.
So this analysis does not specialize to the quadratic.
I'm not sure what you mean by that. It does give you do get the same rate. Let me say this.
Sorry, the step sizes don't specify to the ones you get from the quadratic.
They do not agree, exactly. They're a little bit closer to the constant stepsize schedule. You do get the same rate in quadratics because, of course, the worst case rate over the set of all functions is worse than the worst case rate in quadratics. But yeah. Yeah, so good. Yeah. That's why here this number is at slightly different. I guess that would be something like, if I draw to scale, 1.32, something like here would be this one here. Yeah?
Can you say a bit more on the consistent line?
Yeah. Do you have a specific question, or should I just explain in general a little more? Okay, cool. So let me elaborate a little more. So one reason that this worst case optimization over F is difficult is you're looking over the worst case F in a infinite dimensional class. It's all strongly convex and smooth functions. But gradient descent doesn't care about the whole function. It only cares about the x's you see along the way, the corresponding gradients, and function values if you want. We don't actually use the function values just for analysis purposes. So for all iterations, let's say 0, 1 to n and star. I guess for us, n was 2. And so we can, it's possible to actually optimize over the worst case function by instead of just thinking about what's the data you see along the way and enforcing that your data is actually consistent, that there actually existed a worst case function that interpolates this data. And that's these interpolability conditions that go back to Rockefeller and then Jordan to Bull in this particular form. But the main point for us is that these are the sort of valid inequalities. Any function in the function class will satisfy these inequalities. So when you prove a convergence rate, you can use these inequalities to prove your rate. If you're familiar with like SOS and IQC, this is very much of the same flavor or in the same spirit that you're combining valid inequalities to prove a certain thing is, for example, non-negative.
So you don't have to look at longer than 2 steps of the problem. So this is you only do this for n to solve this optimization.
For now, we're just talking about 2 steps. Later, we'll talk about general n. Okay? Yeah, please.
In the quadratic case, you use the linearity to argue that the order doesn't matter.
Uh-huh.
The non-linearity in the general convex case, is that the reason that the order now does matter?
Yeah. Yeah, exactly. Yeah. Doing a short and a long does not get you to the same place as a long and short. Exactly. Okay, great. Thanks for the questions. So again, this was the n equals 2 case. At this point, it's natural to ask, what if you could do n equals 3, n equals 4? Maybe you get faster and faster, more and more speed-ups. Can you do this for arbitrarily large n? How much faster does this get you? What are the optimal step sizes? So let me provide some description of the prior work. So as I mentioned before we started, there was no result that showed you could get any improvement over the constant step size schedule in any setting beyond quadratics. In my thesis, we looked at this question of hedging step sizes in a number of different settings. I'll highlight that for separable functions, for example, there we showed that you can actually hedge in a different way with random step sizes from a certain explicit distribution. And this actually gives you the fully accelerated rate. I like this result, but I'm not going to talk about today for time. I'm just going to focus on the setting we've been on for all of today. So we'll stick with the strongly convex and smooth setting. Here I already told you the 2-step, and in the thesis we also computed the optimal 3-step. And this gives as I mentioned, the first improvement by even a constant factor. The challenge for larger n is that the search for optimal step sizes is a very non-convex problem, and it's computationally difficult. So we saw some intriguing things for larger n, but at some point we thought it might be good to do something easier, and I got a PhD instead. But in the years since, there's been some very nice, very related developments. So Shuvo here with Bart at MIT and Ernest developed a branch and bound methodology to numerically do this search over, this non-convex search over, to find good first-order algorithms. Their framework is actually more general. It's about first-order algorithms. As a test case, they looked at this problem of finding the best step sizes and used MIT's supercomputer clusters to solve for much larger n, all the way up to n equals 50. So this gives the larger n you get, the better constant factor improvements you get. Very recently, over the summer, Ben Grimmer built upon this branch and bound methodology to round the numbers to rational numbers to rigorously certify these rates. And he did this for approximate schedules up to n equals 127. The step sizes there are not optimal, but because he's solving for much larger n, that outweighs the non-optimality, and this lets you get slightly better constant factor improvements. Let me emphasize at this point that all of these bounds are constant factor improvements. It was unclear whether asymptotic improvements were possible at this point. In fact, Shuvo's paper conjectured some asymptotic acceleration, a polynomial amount, a certain polynomial amount, by fitting a regression to how fast you're getting from n equals 50. Ben conjectured a different amount. Interestingly, even though he solved for larger n, he actually conjectured a slower asymptotic speedup, logarithmic instead of polynomial. So it's unclear whether either of those were true, whether some asymptotic acceleration would be possible. So our recent work showed that actually you do get asymptotic improvements. It's actually a polynomial amount. It's actually even larger than the conjectures. So you actually do accelerate a bit. And I'll tell you about these in a second, but this is basically by solving the same two-step optimization over two step sizes now for n step sizes. And I'll show you this later, but just want to emphasize this is exactly the same two-step solution, just on steroids. You just do it recursively at every scale. That's how we construct our n-step thing. Okay, so let me state our result formally. So these are the Silver Stepsize I'll tell you about in a second, but this is what you get from them. For the setting we've just been talking about, you get a number of iterations. That's O of kappa to the log base rho of 2. So here, rho is this fundamental constant, 1 plus square root of 2. It's called the Silver ratio. I'll tell you more about that later. So this is some number log base rho of 2. If you want the decimals, it's roughly 0.78. This is in between the unaccelerated rate, the slow rate, which is, again, the best thing you could, that was previously known for gradient descent if you don't actually change the algorithm, if you just change the step sizes. And also between Nesterov type rates, which if you actually change the algorithm by adding momentum or other internal dynamics. So we show you can actually accelerate by more than just a constant, and we believe this number is the right number in between. I'll mention briefly that, so I alluded to this before, but the same things extend to other settings. It's conceptually identical. If you remove strong convexity, there you get similar acceleration. So there the whole game is between 1 over epsilon to 1 over epsilon to the 1/2. Again, the same power as you're going between 1 to 1/2. And here you get the same acceleration log base rho of 2, which again is the same decimal 0.78. So those are our main results. Let me mention that there was concurrent work by Grimmer, Xu, and Wang, which they proposed slightly different step sizes, and they got slightly different weaker rates. Their numbers were 0.947, some specific decimal points. This is slightly better than the power 1, not quite as good as the 0.78, or really the fundamental, I think, the right answer that we have here. They mentioned, so they wrote in their paper that there's fundamental obstacles for using their analysis techniques to getting the rates we have here. Okay, so those are the main results. Any questions? Otherwise, we'll move to, I'll actually tell you what the Silver step sizes actually are. Yeah, please.
How does this approach work if you don't really know, if you make a mistake in the strong convexity and smoothness parameter? How do they compare? Is that you put the wrong small n and wrong big n?
Mm-hmm.
Vanilla, like a 2 over n plus n compares to choosing carefully your schedule. What would happen in that case?
Good. So there's a lot of interesting questions, and I was going to mention something related to these things at the end. There's a number of interesting questions related to this. So one part is stability, and if you don't know big M and little m exactly right, how good is your convergence rate? There's other questions about what if you don't know big M and little m at all? Can you adapt over time? So the whole point of this is a new mechanism to acceleration, or a different mechanism. For the more standard, like Nesterov type style, momentum type style acceleration schemes, there are well-established ways of showing stability or instability, as well as doing adaptation. We haven't looked into those. Well, I'll say some of this is active work, but the hope is that one can combine those two things as seen as somewhat orthogonal. But yeah, it's a very interesting question, be important for real-world practice. Yeah.
So is there a connection of this with this like coupling of gradient and mirror descent that I guess it also achieves the full accelerator?
The paper by Alan Zunarecchia? Yeah, so that would I would classify as more of the momentum type style. It has extra state and stuff like that. So I conceptually think about that as somewhat similar to Nesterov.
But can you apply this thinking there? Is there have you looked at maybe something?
If the question is, can you simulate our algorithm by using an extra state, then I'm not aware of such a result.
Is there, I guess you have two sequences.
Mm-hmm. Good.
Certainly you can't go beyond square root k, but like maybe in some more structured settings.
I see, that's your question. Yeah, so I think you already answered it. I was just going to say what you said in the last sentence. Yeah, so for general strongly convex and smooth functions, there are classic lower bounds, oracle lower bounds due to Nemirovsky and Yudin in the 80s that say that square root of kappa, and they actually have the precise constant, and actually recent nice work by Taylor and Drury has pinned down exactly the exact constant, and they know exactly how to, there's no gap anymore for at least that set of functions. If you have, okay. Yeah, this is a game people play, and it's and if you have more structure, you might hope then there might be a bigger opportunity more than just a constant. Good. Okay, so thanks for the questions. Let's okay, so what is the Silver ratio? 1 plus square root of 2. This is actually a number that comes up in a number of places in number theory and fractals, etc. So one way to define this, or the standard way, is through continued fractions. If you do n plus 1 over n plus 1 over n and so on, or in shorthand this way, this gives you, if you solve the fixed point equation, it's some quadratic written here. And if you plug this in for different n's, you get different what are called metallic means. So if you plug this in for n equals 1, you get the familiar golden ratio. If you plug in n equals 2, you get the silver ratio, the stuff we have today. Someone had too much fun naming the bronze ratio, copper ratio, nickel ratio, etc. These are related to fractals. It would be nice to have some more concrete connections. I'll mention briefly that these things apparently come up in architecture, as something Pablo told me about. We found out later. So the golden ratio is famous because it was thought to be elegant proportions for width and height for drawing humans. Apparently in Japanese architecture, I was told that this is considered a visually appealing ratio between height and width of buildings, and apparently also in Doraemon. So if you want to learn about this, you can ask Pablo or read this architecture website. Okay, anyways, that was a small segue about silver ratio. Let me now finally define silver step sizes. Okay, so this will be, they're fully explicit. There's formulas for this. The simplest way to state this is through recursion. So we'll build the 2n step size schedule from the n. We'll concatenate it twice, but just change a little bit. So hn is the silver step size schedule. H2n is the double one. We're going to write it twice, but then just change the last step size, the nth and 2nth. That would be split. And we'll split it in exactly the same way as we do the two-step thing. So for the two-step, when we go from constant to short and long, it actually comes from solving some quadratic equation, something explicit. And we'll do the same thing here at every scale. Let me explain this for, I think it's easier to explain this for like n equals 4 to n equals 8. So here, we copy over all but the last, so the first 3. We copy this twice, but we don't copy the last step size. We're going to change this last step size. It's the only thing that changes. And we'll split it. The first one will be a shorter version, and the second will be a longer version. And this splitting is the same as the one we have in two-step. Okay? If you draw these, you get pictures like this. So this is for plotted for different condition numbers. So here kappa is 4. Here you have richer function classes, kappa is 16, kappa is 64. For each of these plots on the x-axis, I'm number of iterations. So for example, if I want the 20th iteration and I want the step size, this is how large it would be. And I think this is on a normalized scale. I'll show you the non-normalized scale later. Already from this, you can see a number of sort of, I think, interesting phenomenon. So it's non-monotonic, of course, time varying. You see a fractal appearing. You'll notice that the peaks actually grow exponentially by roughly a factor of 1 plus square root of 2. This is where rho comes into. You'll see that they actually saturate. They get larger and larger. Okay, this is on a normalized scale, but you'll see that they actually they saturate and they don't get too much larger. There is a whole story here that I'd be very happy to tell you about offline, but very briefly, this approximate periodicity, the saturation leads to approximate periodicity for the strongly convex case, which leads to a phase transition in the convergence rate. And that's fundamental. That actually happens is matching upper and lower bounds. But that's a story maybe for a different time. Let me mention that instead, let me focus on the case of when kappa gets larger and larger. So already you can see on this rightmost figure that the saturation is happening much later. In fact, if we take kappa even larger, you might expect that these step sizes keep on increasing unboundedly. And in fact, that's what happens. So when kappa gets arbitrarily large, this means your strong convexity becomes 0, so you have non-strongly convex case. And everything happens conceptually identically. In fact, you can formally take limits. In particular, the step sizes are just the limits of the ones before. If you take this picture and take a limit, you get exactly this picture. So these are the silver step sizes for convex optimization. I've just truncated the last one, so a different number, 63 instead of 64, but otherwise it's the same picture. Okay, so I'm mentioning here that in the non-strongly convex setting, everything simplifies. So here is a different formula for the step sizes. You could write it in the same way with recursion. Here's a different way, which I think is also simple that I'd like to mention. So here you can see the fractal coming out, and this is also a way that you can apparently write this in one line of code. So if you want to plug this into your favorite gradient descent, it's just this one line. This one line gives you these step sizes. Okay, so here the ith step size, again, you could write it recursively, but here's an explicit formula. It's just 1 plus rho. So again, rho is 1 plus square root of 2, silver ratio, to the nu of I minus 1. So nu of I is the two-adic valuation of I. It's a popular thing in number theories is this. If you write the binary expansion of I, this is the smallest power of 2 that there's a 1 in. So of course, binary expansions are naturally fractally. That's why this thing becomes fractally here too. Let me mention that in both this picture as well as the other picture, there is a certain, so just above this, the shortest step is the only step that if you just run, that you actually get a stable convergent algorithm. Everything that's larger by itself would be divergent. And exactly the same thing happens here, because of course these are the same pictures. All the step sizes above here would lead to divergent algorithms by themselves. So it's really important you do the combination, this misalignment. Okay, while we're talking about phenomenology, let me mention a couple things quickly. Okay, so again, non-monotonic fractal order. The largest step sizes now grow exactly by a factor of rho. So this, if you draw these peaks, these are all in proportion of exactly 1 plus root 2 of each other. They become exponentially rarer by a factor of 2, because that's related to binary expansions. So this discrepancy, this ratio of the exponential growth at a factor of rho and how big they are versus exponential factor of 2 and how frequent they are gives rise to this log base rho of 2, this sort of average increase, which is where the rate comes from, at least intuitively. I'll mention the convergence rate is dimension dependent, and yeah. Okay, so these are the step sizes. And so if you put this in here, we get, again, this was the cell we want to focus on today, and this is the what we filled in. So for the silver step sizes, we've proved matching upper and lower bounds. This is exactly the rate you get. We believe this is the best rate you could get from any type of step sizes. Okay, any questions here before we talk a bit more about the techniques? Please.
Yeah, so your very last statement, you said you believe it's the best that can be done. You don't know that yet.
So in the thesis a while back, we computed the optimal n equals 2 in 3 steps. We've actually posted a proof of n equals 2. The same proof extends to larger n. I'd say for now we have a lot of reason to believe these are optimal. I would bet more money than I own, but because it's a recorded talk, let me just say for now that it's, yeah, what I've written here. Okay, good. Okay, then let me mention a little bit about the analysis techniques. My goal here, I'm running 5:15 is okay, right? Okay, more than enough time. So my goal here is not to go in detail about the techniques. I just want to give you a taste for how you might prove something like this, because the proof strategy we have, I think, is quite different, at least from anything I've seen before in this optimization sort of literature. So again, the key challenge, as we've mentioned before, is that we want to look at the progress of all the steps at once, not just the progress of individual steps by themselves. So if you remember the sort of what I called the magic identity before for 2 steps, it looks something like this. You prove an identity, which immediately implies a rate. I'll call this the n-step certificate. So I think back there, this was this tau 1 was rn squared, but same thing. And the key thing here is you need to find these lambda ij's. If you find these non-negative numbers for which this identity holds, then you have a proof. Before I just stated what those numbers are, the point here is to tell you that those actually come from something which is not magic at all. There's a simple formula. There's a certain very simple way of getting this. How you do this is you recursively, in short, and I'll tell you more detail later, you recursively copy two versions of the n-step schedule and then do a small perturbation, because the Silver Stepsizes are the same thing twice, but you just change two small steps. Just change 2 out of the 2 n-step sizes. And I'll tell you exactly how you do that in a minute. But once you do that, then 2 things. First, the n equals 2 case is not magic at all. You get it just from the n equals 1 case, which is the standard textbook, constant step size. And the second thing is once you have n equals 2, the general n is exactly the same thing. There's no difference. Okay, so let me tell you how you do this recursive gluing. So we'll build up to it in 2 parts. So first, let's not actually prove the rate for the Silver Stepsize schedule. Let's consider doing n steps actually concatenated twice. Let's not actually make those 2 changes. So imagine you have the n-step certificate. We have the best rate for n steps. So I'll write this as progress for first n. And this will be progress for second n steps. These are the same things, just the only thing is we're starting from x0 to xn, or xn to x21. You can apply it either way. And a very simple observation is if I multiply the first inequality by tau n, just so I can cancel these terms, and you add these 2 things up, then you get some bound on the 2n step progress. So you have that the 2n steps, it has this rate, tau n squared. We'll talk about this in a second. This is not the right rate, but we'll fix it. And you actually get a formal proof. So if you take these lambdas here and these lambdas here, you get some thetas when you combine them. So here's a sort of a cartoon. Ignore the last row and column. These are boundary effects that are... but the main point is if you take these lambdas from the first n steps, that's between all I and j between 0 to n. You just write those in your first block matrix. And the second one, here I'm just taking care of the sparsity. Here is the other part. This is this part. Then you actually have your theta matrix. This is a valid identity that's true. It proves that tau n squared rate for going twice. The bad thing is this is a sort of a trivial rate. This is exactly the same thing as doing this. We've just gone from r1 to r1 squared, or here tau 1 to tau n squared. We haven't got anything better than sort of this greedy argument. But that's okay because we haven't actually used our algorithm. So there's going to be 3. We're going to take this identity and change 3 things. So the first thing is we're going to change this tau n to tau 2n. That's the whole point of the acceleration. So I was calling it r before. These are just the squared. So from the second thing is we're actually going to use the algorithm. So this thing we just proved was by using the n step twice, unchanged. But we have to change the nth step and the 2nth step. So x2n is actually a little bit different. It's a small perturbation away. And then, of course, we can change the thetas however we want. I mean, this is our multipliers to prove identity. So it turns out that there's a very simple way of changing these multipliers theta that accounts for both these 2 things. You add some sparse corrections and some low-rank corrections. Here's a sort of cartoon of the main point is that there's some explicit formulas. They're conceptually, they come up in very simple places, and there happens at the same thing at every scale. So if you just apply this formula, you get the same thing. You get there's no magic in where the n equals 2 case comes from or general n. So again, the details aren't so important today. I just want to give you at least a sense of how we try to prove something like this. We do want to look at the progress in all steps together. And the way we make this tractable is by using the fact that it's almost recursive with a small change. Okay, so let me finish with takeaways and mention a few other open directions. So the main result today was that If you're careful with your step sizes, this can actually buy you quite a lot. You can get faster convergence. The key algorithmic mechanism, as we discussed, was hedging, this idea that the worst cases can't align between different iterations. And to actually prove this, you have to show that, to prove the function can't misalign in different iterations, you have to use rigidity of the function. You have to enforce long-range consistency conditions between early iterates and later iterates. So those are the three main takeaways. I think we're just scratching the surface here, so there's a lot of interesting questions. Some were already mentioned before, earlier in the talk. There's a number of questions related to if you have restricted function classes. So there's a question before. So if you have, for example, I mentioned if you have separable structure, then there's a different, a related mechanism for acceleration. We showed that you can use random step sizes from some distribution. This gets the full acceleration rate. There's other really interesting questions, multi-scale structure and things related to this. There's questions related to robustness, as alluded to earlier. It's a natural question to ask. We use some very, very large step sizes. Is this not robust? Is this robust? To what extent is this robust to misspecification in the gradients or to floating point arithmetic? So lots of interesting questions. My group is actively thinking about a number of these. There's also connections to empirical phenomenon in neural networks. So this is not exactly my field, but I've been told that in the last half-decade there's this very interesting phenomenon called superacceleration, where people use periodic step sizes, and they've empirically observed that this leads to faster convergence in a number of settings. I think the type of step sizes that I've talked about today are sort of the only things or the closest things to that type of periodic choice, and I don't exactly know how the connections could be precise, but at least maybe this could give a start to what bridge there might be. So there's interesting questions there, a lot of other interesting questions. Let me finish on just one in particular. So this talk, I phrase is all about gradient descent, but I actually don't care about gradient descent at all. What I find exciting, or what I'm interested in is not that this is about gradient descent, not that we have faster gradient descent, but that there's an opportunity if you, for faster convergence, if you look at multiple steps together. If you open any optimization textbook and look at almost any algorithm analysis there, they all go through one-step type analyses, because that's what's tractable. I told you how to improve that for gradient descent today, but I think this happens for every algorithm, and let me just say I think this warrants reinvestigating sort of a broad spectrum of optimization algorithms. Thanks. Please.
Those multipliers, are they computer assisted generated? Is there a reason those fall out?
Good question. So we have explicit formulas for them. They're explicit rational functions. We can compute them formulas for recursive or just all at once. So you don't need a computer. In our paper, we never write the word STP, I think. Certainly, computer searches really helped us guide the search. Yeah, does that answer your question?
I guess what?
Oh, if you're asking where these numbers come from,
Why should those multipliers?
You'll have to wait till the optimality to release a little bit more magic. So I'll tell you more about that soon. Thanks.
Can you say a bit more about the dependency in dimension? You said that you showed that parity converged in some ways.
Yeah, good. So the standard convergence of gradient descent and also for accelerated methods are all dimension independent in that the iteration complexity doesn't depend on dimension. This is because, these extend to L2 if you do it the right way. The point here was just that the same thing happens for us, nothing, just as you'd expect. And the reason this comes, or where you see this is because the only part where you have the dimension, where you have the function dependence is these interpolability conditions, the conditions for some data to be interpolable by convex function, and this holds in L2. So, anyways, this is more of just an observation that what you'd expect actually happens.
Right.
Yeah.
I guess my question was
Good question. Yes. Let me say just a couple things. This is something also we're thinking about. The results we had back a while ago for separable one-dimensional functions are separable, trivially. For one-dimensional functions, what this result says is you can get the fully accelerated rate, root kappa, by actually just using random step sizes, ID, every time from a certain distribution. It is natural to conjecture that there is not a fundamental gap that goes automatically from dimension 1 to dimension 2, and that there should be some scaling in the dimension. That is a much harder problem that I'm happy to tell you about more offline. Good question.